All right, hello everyone. This is the second part of our class number 18. We are covering the decision trees theory. I believe we stopped here. We talked about Gini, cross entropy, and error rates. Now in practice, we don't use error rates, but we'll be working with either Gini or cross entropy. Gini and cross entropy, when it comes to the classification criteria, they're pretty much the same, but it's good to know that cross entropy is more sensitive to purities or impurities when we are closer to p is equal to 0, equal to 1. But in practice, most of the time, their performance is really close to each other. All right. Then so here, let's look at you're looking at the decision trees versus linear models, right? So there are many times that our simple linear regression model, the OLS, the OLS engine is outperforming many machine learning models. But when we have the luxury to observe the data, right? So when the data is low dimensional, if you can plot the data and look at for example, we are dealing with something like this. And if the true relationship, if the true boundary is linear, so on the top, the true boundary is linear, right? So we have green and let's say yellow. And as you can see, the true relationship, the true boundary is linear, right, on the top. Then here we're going to use simple linear regression model, right? Well, this is classification. Let's call it logistic regression versus decision trees, right? So these are the decision boundaries for let's say logistic regression. This is a decision boundary for decision trees, right? As you can see, this model is going to perform a lot better than this one. Why? Because the true relationship, the true boundary is linear. So whenever the true boundary is linear, you should not try the decision tree, right? Because we know that logistic regression is going to be doing a perfect job. On the other hand, if the true relationship is nonlinear like this, look at that. This is a true relationship in the data. And then in this case, if you use a linear boundary like logistic regression or MMC, maximum margin classifier, there's a good chance that it's not going to do a good job. So you have to use some nonlinear decision boundary. You can do KNN, you can do SVM using the RBF kernel function, or we can, in this case, in this very exaggerated case, it's going to be best if you use decision trees, right? Because it's just going to classify everything perfectly, right? So why do you always do that? So why we don't always do that? So look at the plot, look at the data, decision boundary in the data, and say, okay, which one is going to do a better job? So what's the answer? What do you think? The answer is very simple. Just think about it. We don't know, right? Because we don't have the luxury to visualize the data like this. Imagine the data is in high dimensional. So just keep in mind in practice, if you're working with a data set which has only 2 dimensions, 3 dimensions, try these things first, right? Don't overcomplicate the problem. Try to visualize it first. And then if the data has millions of records, make sure that you work with a subsample of 10,000 and you can observe things, especially if the dimensionality is low. And then you try to make an educated guess before blindly applying machine learning models, right? So this is really important application. All right, now the third part of the theory for the class, pruning a tree and tuning hyperparameters. Let's talk about the concept of pruning a tree. What does that mean? I think I need to put it in slideshow. Okay, yeah. Decision tree may produce good predictions on the train set, right? This is a fact. We know that decision trees may overfit, especially if you do not define stopping criteria, right? But it is likely to overfit the data, leading to poor test set performance. And we know the reason why. So if you have a good performance in the train set, why do we have if you're overfitting, why do we have a bad performance in the test set? You have to say something about the bias. Bias is high or low? If you're overfitting, bias is low, but the variance is high. So if you work with the test set, because the variance is high, the performance of the model in the test set is going to be poor, right? So we know that this large trees, there's a good chance that they're going to overfit the model, overfit the data. So maybe, and then if I ask you what's the solution, maybe the simplest answer that comes to your mind is that, okay, let's work with a smaller tree, right? Why working with the very bushy tree? Let's work with a smaller tree. Let's see what's the caveat with that. A smaller tree with fewer split may lead to a lower variance. That makes perfect sense and better interpretation, but at the cost of little bias, right? So guys, remember where we are. I have to draw something for you here. Let's call it, this is the number of, I'm just showing with the absolute value. This is the number of terminal nodes, right? From left to right, the tree is going to become bushier and bushier and bushier. So we have complexity. So from left to right, the complexity of the model, the decision tree is increasing. So if the complexity is increasing, what is this one? This is my bias square, right? What is this one? This is my variance. Are we good? So there are decision trees. Do you agree that the decision trees are somewhere here? Especially if the stopping criteria is not that restrict, right? So the decision trees are, the bias is very small, but the variance is very high. And here we are suggesting that maybe we should reduce the number of bushes and then work with a smaller tree. If you work with a smaller tree, yes, the variance is decreasing, but the bias is increasing, right? And that's not the only problem. Let's see what's a bigger issue with that. Are we good in terms of where we are in terms of bias variance? Okay. So this strategy may result in smaller trees, but it is too short-sighted. So here I bring a quote from Tipshirani Hasty, actually the main textbook, Introduction to Statistical Learning. It's very powerful. Look at that. It says that a seemingly worthless split early on in the tree might be followed by a very good split, and a split that leads to a large reduction in RSS or impurity index later on. Okay, so if you work with these small trees, there's a good chance that you're missing those better splits down the road, right? So this is a caveat of working with small trees. Does that make sense? So what's the solution? Look at these 3 bullet points. Very bushy trees, we know what's wrong with that. The variance is high. Very small tree, you're somehow ignoring those good split down the road. So what's the solution? What do you think? Imagine back, it's 1980 something, and you see this problem, and you want to develop your own model, right? So what's your solution? What do you think? How can I have the best of 2 worlds? Can you what?
So can you cut out the worthless splits without?
Oh, well, actually, that's a very good observation. No, but no, historically, you're not there yet. No, you jump into the very last part. That's the idea of boosting. We were going to talk about it, but that was a good observation. What else?
I was going to say something similar of combining the splits to find a different measure that you split off of, but that can be very difficult to do.
Yeah. Well, actually, you're both of you are on the right track. I'm glad that this is beyond what I expected, honestly. So because the answer is, well, at least let me see if I can make it full screen. Yeah. Well, the idea is that let's make a very bushy tree at the very first step, and then try to prune it back. Okay. So let the algorithm see all the splits down the road and see which splits are good. Make sure that we are not missing those good ones, and then we start pruning back the tree. So this is called pruning a tree. And what you were mentioning, be more smart and then somehow ignore the worthless split down the road. So that's the idea of boosting, and that's genius. Okay. Yeah, we'll get there too. So we are looking at decision trees, and then we prune these decision trees. And next class we're going to do random forest, and next class we're going to do boosting. So we are improving these decision trees step by step. But for now, let's start with the very basic one. So a better strategy is grow a very large tree. We call it T null or T0, and then prune it back in order to obtain a subtree. Okay. And we do that by something called cost complexity pruning. Okay, so look at the term and try to think about it. Cost complexity pruning. What are we doing? So cost, you can think of cost as penalizing. Complexity pruning. So we are penalizing adding more complexity to the model. So you have to think of it like this. Let's rewrite the objective function. Remember, in regression, what was the objective function? Minimizing the RSS, the summation of the RSS, right? How can I how can I play with that objective function in a way that if I add more trees to the model, it should penalize the objective function? Does that make sense? So how can we do that? We have something like this in our simple linear regression. So imagine we have linear regression and we added a penalty term. So we went from linear regression to penalized regression. MMC to SVM, exactly the same concept, right? MMC, there was no slack variables, and then we went to SVM by adding those slack and penalizing the objective function. So here we're going to do exactly the same thing. We're going to say that the objective function is RSS. Let's penalize it by a term that if I add more trees, more branches to the model, it's going to increase the RSS, which is a bad thing. And the algorithm is minimizing the entire thing. Does that intuitively make sense? Okay. So this is the answer I expected, but you outdid my expectation. Okay, so consider a sequence of trees indexed by non-negative tuning parameter alpha, and then each alpha corresponds to a subtree which belongs to the bushiest tree, right? Remember, we said that they start with the largest tree possible, and then we want to prune it back. So here's the objective function. So this is something that we have seen before, right? This is minimizing the sum of squares in each region, then add them together, right? So I have a sum of square RSS here, I have an RSS here, or MSE, it really doesn't matter, guys. And then if I add them, I don't know, region 3, region 1, region 2, if I add them together and minimize the entire thing, the algorithm is going to find two things: which feature to start with, where to put this plate, right? But now we are adding this term. This is our cost complexity pruning part, right? The method is called cost complexity. So the absolute value is T is the number of terminal nodes. The number of terminal nodes. So for example, here, this is a tree. So how many terminals do I have here? 2. Here, how many do I have? 3. Here, how many do I have? 4, right? So these are the number of terminal nodes. And basically, if alpha is 0, if I set alpha is equal to 0, and if I do not put any other stopping criteria, the tree is going to become the largest possible because we are not penalizing it. Then I say that, okay, increase this alpha. If I increase the alpha, we know that the algorithm is trying to minimize this thing, right? And this is a positive number, and this is a positive number, and it's a bad thing, right? This is bad because it's a minimization. You're penalizing this minimization by adding a positive term to that, right? Now imagine alpha is super large. If alpha is super large, you're going to get a very small tree, right? Because it's penalizing adding more branches a lot more. Does that make sense intuitively? All right. And these are the regions, and these are the predictions in each region. So just as a reminder, y hat, for example, y hat R3 is my y bar in the third region, right? Okay, so this is very genius, right? This is a really intuitive solution to this problem. And then how can we figure out what is alpha? What's your guess? This is a hyperparameter. How can I tune that? Cross-validation, right? At the end of the day, I can plot different alphas versus if it is regression, RMSE, if it is classification, accuracy, and then look where if accuracy is max or RMSE is minimized, right? So it's easy to figure out what's alpha, and we're going to do it in Python. Alpha controls the bias variance trade-off. So as a reminder, so you help me out. If alpha is equal to 0, what is bias? High or low? Bias is low, right? Yeah. Because this is a bushiest tree, and variance is high. And if alpha increase, the other way around. Okay. So these are all the good things, and about this cost complexity pruning method. And finally, when you found that alpha through cross-validation, we go back and refit the entire tree, and we figure out what was the optimal max level for that tree, right? We're going to do it today. Okay. So here's the slide from the ISLR textbook. Actually, the next couple of slides are from the textbook. And I just leave it here for your reference. This is the algorithm. We talked about it, but if you want to have it in a nice, I don't know, step like this, you can take a look at this slide. Basically, it's summarizing the recursive binary splitting process. And then we said that, okay, grow the largest tree, then apply the cost complexity pruning, and then use k-fold cross-validation to find the alpha, and then refit the model and find the corresponding number of terminal nodes for that tree, right? So this is very straightforward. Okay, so imagine we applied this pruning process, right? Cost complexity pruning process to our data that we worked with last class. So this is the baseball salary data set, right? And again, these slides are coming from the textbook. And we already saw that visually. We saw that if I have 3 regions, that would be the best, right? Do you remember from our previous classes? So we know that maybe terminal nodes, if the number of terminal nodes is equal to 3, that's the best outcome. But let's let the algorithm decide, right? Because that was something that we visually were happy with those splits. But let's see if the algorithm suggests the same thing. So this is an unpruned tree, right? Resulting from the recursive binary splitting. And as you can see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have 12 terminal nodes, right? So we have 12 regions. So our data is not like this anymore. I don't know, was it like this or the other way around? I don't know. I think it was like this. It's not like this anymore. It has 12 of these splits. I don't know. So this is an unpruned tree. This is unpruned, but it doesn't mean that we don't have a stopping criteria, right? Because I believe there are 150 observations in this data set. And then they're using the criteria that at least the number of samples in the terminal node must be greater than 10. Because if I do not put this criteria, the tree can be even larger, right? But we don't, usually you don't want to, because if I do not put even that stopping criteria, it is guaranteed that the model is overfitting, right? Let's say you have only 1 sample at each terminal node, the RSS is zeros, but what's the point? You're absolutely overfitting that, right? So I think even the default inputs in Python, it has some stopping criteria. Okay, so we start from here, and then what we do, we apply the cost complexity pruning method, and we use the cross validation to find that number. So I want you to focus on the green one. So the green curve is we are looking at mean squared error versus alpha. This is literally alpha, but in the textbook, it's relating it to the tree size. There's a 1-for-1 relationship between alpha and the number of terminal nodes. For each alpha, there is a specific number of terminal nodes. So we can plot alpha versus MSE or number of trees, the number of terminal nodes versus MSE. In the Python part, I'm going to plot the RMSE versus alphas. And then we refit the model, we figure out what was the max depth of that tree, right? But I think just for simplicity, the textbook says that instead of alpha, let's look at tree size, because each alpha has a corresponding tree size. Does that make sense? Okay. Now, I want you to focus on the cross-validation. So the train set, we are not interested for sure, because we know that for a fact the train, this is going to decrease for train set. For test set, I wish it was observable, but sometimes it's not observable to me, right? And even if it is observable, it's not fair, right? Because you want to make sure that you are not tuning the hyperparameters by leaking information from test set to the model, right? So the solution is going to be cross-validation. If I look at the green curve, you tell me what is the optimal what's the optimal tree size? Then when I say tree size, we're talking about number of terminal nodes. That's 3, right? Does everyone see that it's 3? Okay, so it's minimized here, and the number is 3. And if you go back to so this is what the cost complexity pruning suggested, and it is consistent with what we saw from day 1. Does that make sense? But again, don't think that you can trust your eyes more than this kind of algorithm, because here we were lucky because data was super separable when it came to 2 dimensions, and said that, okay, visually it should be like this. But here we saw that the cost complexity pruning was perfectly able to pick those optimal number of terminal nodes, right? So 3. All right. So now let's talk about tuning hyperparameters. What are the hyperparameters in decision trees in general? We know that to avoid overfitting, we can use some regularization parameters, right? They can be added to the model. And one of them we already have seen, this one, alpha. This is our cost complexity pruning parameter. So we know what's the role of that. Let's talk about the rest of them. So the first one, minimum depth of a tree. So if I say that, for example, maximum, sorry, not minimum. the maximum depth of the tree. So if I say that the maximum depth of the tree is 1, so this tree is definitely it's not going to overfit, right? It's going to underfit if anything. So you see that this is, in order to avoid overfitting, we can use that one, right? If I say the max depth is 2, my tree can be something like this, right? So I avoid getting those bushy trees. The second one, minimum population at each node. So this is somehow close to the one that we talked about here, right? So, but it says that minimum number of observation in each node. So at each node, you can say that what's the minimum sample size that we need at each node, right? So if I say that, for example, let's say we start with 150 here, we get, I don't know, it's not symmetric, maybe 60, 90 here. And then maybe, I don't know, maybe 70 something, 20. If I say that at each node, I need more than 30 observations, it's not going to go down this path, right? It's going to make it a terminal node. Does that make sense? Okay. The rest of them are exactly the same thing. So maximum number of decision nodes. So this is if you specifically want to say how many nodes do I want to have, right? Obviously, I can I can control the overfitting, and then minimum impurity decrease or the information gain. You want to make sure that if your impurity decrease is at least greater than this number, then go ahead and do that. If your impurity decrease is just slightly changing, it's not worth adding more trees to that or more branches to the tree. Does that make sense? Why? Because if you're already here, adding more trees, making it more complex, it's going to reduce your bias a little bit, but increase your variance a lot. So it's not worth doing that. Okay, so that's basically the idea. Okay, alpha, we talked about it. What other hyperparameters do we have? We have criterion, which is Gini, entropy. These are the two ones that by default in Python we can use. And splitter. Splitter is basically where to put the split first. You know, best is the one that we talked about in class. Random, you know, sometimes we know that if the data is super large and you want to manage the speed of it, you can do random, and the tree can start from a random point from a continuous random variable. And this is awesome. Class weight. So this is new. Balanced versus non. So any guess? What is this class weight? Imagine we have imbalanced data set, 95.5%. So in decision trees, we can, usually we do it in random forest and XGBoost because we are working with thousands of trees and we can simulate the data in whatever way we want. We can oversample, undersample, something like that. But the idea is that if your data set is imbalanced, 95% default, 95% non-default, 5% default, there is a tuning parameter that says that, okay, undersample it or oversample it, and it's going to do it automatically for you in Python. Okay, so this is really cool. We're not going to do it in decision trees though, because when it comes to random forest, we know that we are working with thousands of trees, and there we can make sure that, for example, if there's a group in the dataset which is underrepresented, let's say 5%, I'm building up thousands of those trees, so I can synthetically oversample those specific group, right? Does that make sense? All right. And by the way, here is a regression in in 2 dimensions, but there's only one explanatory variable, and the other one is your target variable, right? So if I want to use simple linear model, this is the answer, right? If I want to use polynomial model, maybe I can get something like this. And if I want to use decision trees, I get something like this, right? So look at the blue curve versus the blue step function versus the green step function. In the blue one, the max depth is 2. In the green one, the max depth is 5. So max depth is 2. So we are here. Let's say this is level 1, level 2. How many terminal nodes do I have? 1, 2, 3, 4. How many predictions at most we can get out of this tree? How many? So the model is going. What are the outputs of the model? This is a continuous random variable, right? The outputs can be at most 4 numbers. Does everyone agree? Because at each region there is an average, right? Are we good? 4 numbers. So it means that if I want to use a step function, at most, the algorithm is predicting 4 numbers. Do you see that? At most. Why do I say at most? Because there is a chance that we don't go, oh, we can end up like this, depending on the stopping criteria. This is 3 numbers, not 4 numbers. Look at 5. So let's say if max depth is 5, at most, how many numbers can the model predict? 2 to the power of 5, right? These we are talking about binary trees. No, look at that. Well, we have to do the math again. We get the idea. What? 1, 2. I need 1 more level, I believe. So 1, 2, 3, 2 more levels. But you get the idea. It's 2 to the power of 5, 32, at most 32 terminal nodes, at most 32 numbers for predictions, right? So my step function is going to have at most 32 level. 1, 2, 3, 4, 5, 6, 7, 8, 9, you name it, right? So here, maybe it's not 32 because there's a good chance that some of these branches don't go all the way down. Are we good? All right. Okay, last part. So in last part, we talk about pros and cons and application in finance. So let's talk about, I want you to pay very good attention on this slide, because at the end of the day, these kind of things, these pros and cons, which by the way, Ryan and the TAs are going to help me out with putting together a cheat sheet for the course. Thank you. When and where to use which of these models. So we have to basically look at the pros and cons and decide, right? So decision trees are very easy to interpret and visualize. We already know that, right? So because it's even more interpretable than the linear regression. Think about it like this, if you show me a tree, there is no guess. I know that if age is less than something, I go to this branch. If DTI, debt to income ratio, is greater than something, I go to that branch, right? I don't need to, the interpretation is really, really straightforward. It can easily handle categorical data without the need to create dummy variable. Don't you like it? This is really good. Let's say, no, in our New York property data set, do you remember how many dummy variables we ended up with? It was a lot, right? 800 something. Because we had lots of categorical variables that we had to make them dummy variables. In our previous homework, we had a variable year built, right? And the year built has 130 different years. If you make it into dummy variables, you are adding 130 dimension to the data, which is insane, right? For decision trees, however, we don't need to do that. Why do you think that's the case? This is important. Why do you think in decision trees we don't need to translate our categorical variables into dummy variables? Think of a very simple example. I don't know.
Is it because when you do a decision tree, even if it is a numerical value, you're taking like greater than X or less than X, and so it's almost creating a dummy variable in that.
Yeah. Well, basically, it means that we are not saying that, for example, let's say we're talking about GPA letters A, B, C, D, right? In regression, if you translate A to 1 and D to 4, so it's as if 4. Let's do the other way around, 4 to 1, right? 4. So A compared to D doesn't mean that A is 4 times better than D, right?
Right.
So decision tree. So for that reason, we make them dummy variables. But in decision trees, we don't make this comparison at all. It's either A, B, C, or D. Let's call it 1, 2, 3, 4. You're not saying that 4 is twice better than 2 or something like that. So for that reason, decision trees can easily handle categorical variables. So just keep in mind. And guys, remember, if decision trees can handle them, it means that random forest can handle them. So if you're dealing with a problem that if you make the categorical variables into dummy variables and you ended up with thousands of dummy variables, don't do that. Random forest is going to do a better job. Okay. And in short, well, but we're going to talk about scaling in a second. Can easily capture nonlinear patterns. Why? Where do I get this nonlinearity? So in linear regression, nonlinearity came from the fact that if I have, for example, x and x squared, x cubed to the model. In SVM, I'm adding the RBF kernel to the model, and et cetera, et cetera. In decision trees, where do you see that nonlinearity? What is capturing that nonlinearity? Think about it. Guys at home. Let me give you a hint. is there a chance that I see one criteria down the road, down the tree multiple times? So for example, if I say your homework, you're going to see if your FICO score is less than 750, I go down the road and then I look at your income, let's say less than 50K. And then again, I can split the FICO even further. So the FICO down the road has appeared multiple times. So this means that I'm capturing the nonlinearity, right? Does that make sense? This is exactly what neural networks, by the way, behind the scene, the neural networks are capturing as well. It's a lot more flexible than decision trees. So for that reason, when it comes to prediction, neural networks, most of the time, are going to outperform the tree-based models. All right, the next one, it can handle data in raw. So these are very good pros, or very good advantages. We like all of them. So it can handle data in its raw form, no pre-processing needed. This is insane, right? It means that I don't need to do scaling. I don't need to be worried about scaling. Why? Why do you think that's the case? For the categorical, so for the categorical parts, that's it. But actually, the reason is not necessarily the same. Think about the scaling. Imagine we're talking about continuous random variable.
Well, it doesn't matter if you have outliers or not.
No, it's not about outliers. You're in the right direction though. So just push a little further. So why do you think? Let's say I have wage versus education. Wage is $1 million. Education is in years, and I don't care if the units are way different. Yeah. So why we don't care? Look at the algorithm. When we were concerned that these scales are different, whenever you were computing the distance of the observations, you're not calculating distance. Because we are not calculating any, we are not working with Euclidean distance, Manhattan, or whatever, because we are not calculating those distances, means that in decision trees in general, we are not worried about different scales of random variable. This is a very big plus. Okay, guys, there's a reason that random forests and XGBoost are the best decision machine learning models out there, because of all these positive things. And finally, it has no assumption about the distribution because it's a non-parametric model, right? So it's non-parametric. We are not imposing any restrictions on the functional form. What are the disadvantages? Poor level of, so these are all good, and then you're kind of pissed off. Oh no, poor level of predictive accuracy. So this is the bad news, but the good news is that we can get around that, right? We can get around that poor performance by being a little bit more smart. And what we're doing is, guys, I want you to, I'm going to revisit this curve next class. Decision trees are here. The bias is very small. Variance is very large. We're going to say that, can I do something that I start with a very large tree? I do not prune it back, though. Can I do something that I start with a large tree, the bias is small, and somehow can I stick to the small bias and somehow reduce the variance? This is exactly what random forest does by bootstrapping from the data, right? So remember, guys, we're going to talk. Let's talk about the next class. Why bootstrapping is going to reduce the variance? I think it was one of the questions in the quiz for random forest. I asked you, why do you think that the variance is decreasing? So you have to put your statistician's hat on and then think about it. So why, when we are doing bootstrap, the variance of your estimator is going to decrease? That's the theory behind the random forest, right? And then next step, you will be even smarter than that. We say that, you know what, do not grow the tree to the largest amount and then try to use bootstrap. Start smartly, like Ryan was suggesting. Make sure that whenever you're extending your tree, you're doing it in a clever way. So that's what boosting is doing. So boosting is connecting all these things using the bootstrap and adding branches to the tree in a smart manner. So this is what boosting does, right? So I hope that you get the big picture of the difference between decision trees, random forest, and boosting. But we're going to talk about the details on them later on. So we can completely get rid of this one. So this is a good part. However, again, be careful. If you want to sit in front of a client in finance and then plot a decision tree for it. So you have to use the decision tree. So you get what are the pluses, advantages and disadvantages. All right. So this can be done by bagging and boosting algorithm. And bagging, by the way, random forest is a subsample of bagging. We're going to talk about it next class. Okay, so applications in finance. In enhancing detection of fraud in financial statements and generating consistent decision process in the equity and fixed income selection, this is really huge in finance. I'll give you an example. Simplifying communication to the clients makes sense, and portfolio allocation problems. So basically, you want to say what percent is equity, what percent is fixed income, and within each class, which is which. So imagine you want to sit in front. So lots of these robo advisors, what do? They take simple questions from you, right? So imagine you want to. I think I had an example written somewhere. I thought about it. Yeah. So we can start with A. So they say that if you hire a financial analyst and then basically you want him or her to manage your portfolio, the first thing that they do, they ask some basic questions. What's your age? What's your risk tolerance? What's your long-term, short-term liquidity needs? Things like that, right? So let's say age is less than 60. The answer is yes, no. And then the second question, maybe they look at your risk tolerance. So this risk tolerance itself comes from a complete different survey, a questionnaire. Let's say it's high, low, and then maybe they can look at your liquidity needs. Again, it can be high, low. So if it is all low, then say that, okay, you know what, you can invest in 30-year fixed income, maybe. If the liquidity need is high, but your low, risk tolerance is low, you can do a portfolio with shorter duration, right? Let's say, I don't know, 5-year municipal bonds, 5 years, 10 years. And then if your risk tolerance is high, you can go to a higher riskier assets, right? So for these kind of things, you need to have decision trees, right? And then finally, this is an example from the CFA reading, which I highly encourage you to just keep reading. The CFA reading is part of our mandatory reading for the course, right? So make sure that you do the CFA readings. And I took this example directly from the CFA reading. Let's look at it quickly and see if you can make sense out of it. Okay, so what do we have? Imagine that we have only 2 exponential variable. This should be x2. We have IOG, which stands for investment opportunity growth. How many, what is the rate of opportunity growth out there, right? So what other interesting project you can think of, right? And the second one is free cash flow growth. We look at the growth version of that, but I just want you to think of investment opportunity and free cash flow. And so let's say we have investment opportunity here and free cash flow here. This is the data. Can I use a linear separator here? Absolutely no. Right? So what does linear separator do? So either way, I'm going to have a lot of misclassification, right? So what can I do? I can do K and N, but K and N is going to misclassify these ones because they're very close to each other. I can do SVM using the different RBF. SVM is going to do a decent job on this, for sure, but with the RBF kernel. And I can do decision trees. So decision trees, this is what we have. If you want interpretability, you do decision trees, right? So let's quickly look at this one. So imagine we say investment opportunities. So the left is no, right is yes. Investment opportunity, we start with the investment opportunity, right? If the investment opportunity is, well, less than 10%, and then we look at the free cash flow. So we say, do you have more than 10% free cash flow growth or not, right? If you don't have, and the decision is either that company is going to make a dividend or not, right? So that's a decision for the company. So think about it intuitively without looking at the answer. So if the investment opportunity out there is high, right, and there is no free cash flow growth, does that company make a dividend payment or not? Investment opportunity is there, but they don't have free cash flow. So basically they're not going to pay dividend, right? So this is how it's done. And then say, okay, investment growth is high and they have a lot of money, and sorry, the investment growth is low. Sorry, I'm in the wrong slide. So the investment growth is low on the left, and they don't have enough cash, so they're not going to pay anything because they don't have free cash flow, right? But if they have cash and said, okay, investment growth is not greater than 10%, but is it at least greater than 5%? If it is at greater than 5%, say, okay, we are not going to make any dividend payments, right? Because we can exploit that free cash flow a lot better than, let's say, risk-free rate, whatever, or the rate of debts, the cost of debt of the company, right? If not, well, let's pay it out. I have a lot of free cash flow on my hand, and the investment growth opportunity out there is less than 5%. So let's pay it back to the shareholders. Maybe they can do better than the company, right? And you can think of this, we can make same argument for the right-hand side. If the investment opportunity out there is a lot, and if you have a lot of free cash flow, then yes, if your free cash flow is a ton, you can afford to pay some dividend and invest in those opportunities. If your free cash flow is not greater than 20%, you're going to exploit every single dollar that you have, because the investment opportunity out there is greater than 10%. All right, so this was an example. And I believe we answered all the questions from the students. So should we be concerned about the computational expense of MSE when working with large trees of continuous data set? I think, Grayson, we talked about it last class. Having a hard time understanding the Gini impurity and what conceptually that means. I think we are in good shape, right? Gini impurity. Basically, the concept is that it tells you how pure each region that you're looking at, right? You want to get Gini or entropy equal to 0. That's the goal. What is Gini impurity role in classification? What's the role? What feature to start with? Where to put the split, right? So that's the role of Gini. A little confused on how to pick which method should be used for a given data set. Again, we're putting it cheat sheet together, but you have to look at the slides and look at the pros and cons, and then decide on your own that which method is going to do a better job. And then finally, we'd like to go over when algorithm decides to create a leaf node versus continuing the decision tree. I think, Ryan, you got your answer. Basically, those are the tuning hyperparameters. The algorithm does not necessarily decide. You tell it. Okay, you tell that. Okay, I need at least this number of observation in the terminal node, and et cetera, et cetera. Okay, so that's the theory part. And yep, we are going to continue our discussion in the next part for the Python.